Bad bitch, sweeter than molasses. Shit got gliss on my wrist like a maverick. Bitch, she a rich little bitch with some baggage. Shit gotta hit quick, leave her in the past tense. Cause she a bad bitch, sweeter than molasses.
Hello everyone, and welcome to the second lecture on this series on game hacking. I'm Loab, and today I'll be guiding you through the fundamental concepts essential for understanding game hacking. Today we'll start by delving into computer fundamentals, where we'll learn about computer components and gain a comprehensive understanding of our operating system. Once we master the basics of our computer, we'll continue with base systems used in our operating system. Having mastered these foundational concepts, we'll then embark on a more difficult and time-consuming part on game hacking. This part is the virtual memory of a game. This video might be a bit long, but I've worked hard to explain things in a way that's easy for you to understand. It's important to watch the whole thing because the topics we're covering today are key to getting better at game hacking. So without any further ado, let's just get started with the computer fundamentals. You might be curious about why I'm using a computer building simulator for a guide on game hacking. Well, the idea here is simple. In the future, we're going to write code that gives us cheats. To pull this off successfully, we first need to grasp how our computer deals with games. If we don't understand that, how can we ever even create our cheats? So let me break down a few crucial aspects of our computer hardware to get started on this game hacking journey. So what I'm going to do first is I'm going to click on install here, and I'm going to click on motherboards. And the motherboard is basically the main circuit board that connects and allows communication between all the other components we're going to install into this PC. So when I click on install, I can now add more components. And the first component that I'm going to add, which is also the most important component, is the CPU, which stands for the Central Processing Unit. And basically the CPU is the brain of the computer, and it performs most of the calculations and tasks. It is responsible for executing instructions, and these instructions are simplistic and can be a bit different depending on the architecture. Let's say we have an instruction that adds two numbers together. In order for the GPU to do this efficiently, the CPU has several areas where it can store and modify data. These are called registers, and they are a very important term to understand in game hacking. We will learn about this later, but for now, just remember that the CPU is a very important component in game hacking. The next thing I'm going to add is the RAM, stands for RAM, aka the Random Access Memory. So click on install, go to memory, and then let's take this one. And we're going to install it. And RAM is temporary storage that the computer uses to store data that is actively being used or processed. Your game will be loaded into memory in these components, the RAM sticks. The next component is going to be the GPU, other people call it a graphics card, and GPU stands for Graphics Processing Unit. The Graphics Processing Unit is responsible for rendering graphics, and is crucial for gaming and graphics intensive tasks. Without a graphics card, you're not going to be able to play a game. Alright, so the next thing I'm going to install, which is also a very important component but not specifically for game hacking, is the power supply. And basically what the power supply does is it converts electrical power from an outlet into a form that can be used by every component in the computer. You can pretty much forget this part because it's not needed in game hacking at all. Alright, and the last thing I'm going to install is the storage. And these come in like two parts. You have HDD, hard disk drives, and you have SSD, solid state drives. Storage refers to the devices used to store data permanently. HD is slower, but it offers you more storage capacity at a lower cost per gigabyte. While the SSD is faster, it's more durable, and they have become increasingly popular for their speed in data access. Your game, for example, is stored in these storage components, just like your cheat will. As we delve into this program structure overview, we'll explore all the computer essentials for mastering the art of game hacking. If there's a term or a concept within this list that's unfamiliar to you, I highly encourage you to keep watching, as we will learn all about this in this series. In this map, you can see base systems in the middle and virtual memory on the right. In today's video, we will learn all about these two topics. And I'll also cover pointers, as I think pointers are closely related to virtual memory. Alright, so it's time to learn about base systems. But Loab, what is a base system? A base system is a system that is used to represent numbers. There are different base systems like decimal, hexadecimal, or binary. There are many more base systems, but I will cover these three ones, as these are the ones we will be using the most in game hacking. So let's take a look at the three systems. We have decimal on the top, and we know that's the number 10. But now we take a look at a hexadecimal number, and we may get confused. The number 10 in hexadecimal is not the same as we know it in the decimal system, because 10 in hexadecimal is actually 16 in decimal. The same thing with binary. The number 10 in binary is actually equal to the decimal number 2. So how do we know when a number is in hexadecimal or binary? Well, we do that by adding the prefix 0x in front of a hexadecimal number and 0b in front of a binary number. So we now know how to distinguish hexadecimal and binary from each other. But we don't know how we can actually read hexadecimal and binary numbers. So let's get started with understanding how we can read hexadecimal numbers. Okay, so we're going to start with the hexadecimal system. And the hexadecimal system is often abbreviated as hex. Or, just like I've explained earlier, it's 0x in front of your number. A hexadecimal is a base 16 number system, and that means it's using 16 distinct symbols. Take a look at this list. We've got the numbers 0 to 9, which is just the same as we have in our decimal system, but we keep counting up until we have 16 symbols. And then you can see, okay, the number that comes after 9 will be 10. But in hexadecimal, we write it as A. And the number 11 would be B. Alright, and then you would keep counting up until we reach F. If we now count all these numbers, we can see we've got a total of 16 symbols. But that's also why, for example, decimal is base 10, because it knows 10 distinct symbols. In the previous example, we saw that the number 16 in hexadecimal is actually equals to 10 in decimal. But how can we convert a hexadecimal number to an actual decimal number? Well, I'm going to explain that right now in Paint. Alright everybody, so I've got this example right over here. I've quickly written down what I just explained about the hexadecimal number being base 16 and having 16 total characters. But I've also given you a decimal number. And firstly, I'm going to explain something that's crucial to understand before we get started with actually converting an hexadecimal number to a decimal number. And that's being able to understand that this is part of the ones, this is part of the tens, this is part of the 100s, and this is part of the thousands. I'll try to explain this in a more clear way so anyone can understand. The number 0 is the rightmost digit in the number. It's all the way to the right. And it represents the quantity of units for the ones. In the number 1150, the digit 0 is the ones place, indicating that there are 0 ones. So 0, that's like write it a bit more like this, more spacing. This is part of the ones. Like so. Moving one more to the left, we have the tens place. This is the second digit from the right. It represents the quantity of tens. In the number 1150, the 5 indicates that there are 5 tens, because 5 times 10 will be equal to 50. So this is the tens part. And then on the third index from the right, it represents the quantity of hundreds. And in this number, the digit 1 is the hundreds place, indicating that it's 100. So this is part of the 100s. And then the last one is representing the quantity of the thousands. And in this number, the digit 1 is the thousands place, indicating that it's 1000. So the 1000s. And we can write this part in a different way. In base 10, decimal, we can write ones as 10 to the power of 0. because 10 to the power of 0 is equals to 1. And then for the next one, we can do 10 to the power of 1. And 10 to the power of 1 is equals to 10. And then the next one will be 10 to the power of 2. And that's going to be 10 times 10 is 100. And then for the third one, it's 10 to the power of 3. And that's 10 times 10, that's 100. And 100 times 10 is going to be 1000. So why do I actually explain this? Well, it's actually the same in hexadecimal, but instead of using 10 as a base number, it's actually 16 to the power of 0, and 16 to the power of 1, and 16 to the power of 2, etc. So if I get rid of all of this here, and I give you a random hexadecimal number, like 0x f8, and f8 is actually the offset we used in the previous video, but right now we're going to convert this hexadecimal number to a decimal number. And the first thing we have to remember is that this 0x is just to show us that this is a hexadecimal number. So we do not take this into consideration when we're going to calculate. So what we're going to do is we're going to write down f8 without the 0x. And what we're going to do first, we expect, okay, this is part of the ones. So that's going to be 16 to the power of 0. And this one is going to be part of the, well, you would say tens, but in hexadecimal, instead of 10, it's actually the 16s. 16 to the power of 1. You can tell if we do 16 to the power of 0, it's going to be 1. And 16 to the power of 1 is going to be 16. So instead of part of the tens, it's actually part of the 16s. Let's say we have another symbol in our hexadecimal number. Then this would be 16 to the power of 2. The more symbols we add to our hexadecimal number, like let's say we add another one, it would be 16. This base would always be the same, but we would keep incrementing this to the power of number. Alright, but in this case we do not have these numbers. It's just f8. So if 16 to the power of 0 is 1 and 16 to the power of 1 is 16, what now? Well, now what we're going to do is we're going to take a look at this number here, 8. And we're going to this list here. We're going to see, okay, number 8 in the base 16 system is just the number 8 as we know it in the decimal system. So what we're going to do is we're going to write down 8 and we're going to multiply that number by 1. So 8 times 1. And that's going to be 8. Okay, so now we go one more to the left. And we have the symbol F. So then we go again, we go to this list here. And we can see F is number 15. So then you write down 15 times 16. And I've actually calculated that right here. It's going to be 240. So you write down 240. And then it's just as simple as adding these two numbers together. And then we end up with 248. And we can check that actually. We can check if that's correct. You write down F8. And we can see in decimal that's going to be 248. And that's it. That's how simple it is. Alright, so let's take a look at this second example. We now have 3 symbols. And just like we did before, we do not take this into consideration with our calculation. So we're just going to write down 9, A, and C. And we know we calculate from the right and we go to the left. And we know the first character on the right is always going to be 16 to the power of 0. And the second one is going to be 16 to the power of 1. And this one is going to be 16 to the power of 2. And we know 16 to the power of 0, that's 1. 16 to the power of 1 is 16. And 16 to the power of 2 is 256. Okay, so now we're going to take a look at C. And then we see, okay, C is actually number 12. So we write down 12. Then the next one is A. A is actually 10. So we write down 10. And then for the last one, 9, that's actually the number 9, just like we know in decimal. So you write down 9. Okay, so now we have these numbers here and we have to multiply each of these numbers with each other, like so. And then we have, okay, 1 times 12, that's 12. 16 times 10, that's going to be 160. And then 256 is going to be 256 times 9 is 2304. Okay. Let's double check. Yes. Okay. And then the last thing we have to do is we just add these numbers to each other. Like so. And then we get the number 2476. 2476. And we can now check in our calculator. Hex 9AC in decimal is 2476. Sorry, this has to be a 6. Okay. So that's pretty much how you can calculate it. It's very simple. You just have to know this rule. And you have to know that we calculate from the right to the left. That's it. Alright, so before we continue with learning how to convert a binary number to a decimal number, we first have to understand how we actually read a binary number. Like, how does it work? Well, it's actually very simple. Let's take this example with 4 numbers in the binary number. Since the binary system is base 2, we only know the numbers 0 and 1. And let's just take a look at this number here. This represents the number 0. Let's see what the number 1 looks like. We can see we start all the way on the right and we add the number 1. But now, what is number 2? Well, we can see that it shifts 1 to the left. That's going to be number 2. And then let's take a look at number 3. Okay. Now it's also on the right. So let's add one more. And we can see that it's like weirdly shifting to the left. It's shifting, then it's filling, and then it's shifting again. Shifting, filling, shifting, filling. We have this pattern, and that's basically how you can count in binary. All the way on the right, if we just have the number 1 and the rest is 0, it's number 1, of course. And then we go 1 to the left because it's full. And then we fill it again. And then we shift. And then we fill. And then we shift that one. And we fill. And then the total gets shifted again. Alright, so binary. We know binary is base 2, so it knows 2 symbols. And these symbols are 0 and 1. And in this case, 0 means off. And the 1 means on. So let's write down a random binary number, like 1, 0, 0, 1, and 1, 1, 0, 1. And that's it. Okay, so what we're going to do, for this one also, we're going to read from the right to the left. Okay? And what we're going to do is we're going to start all the way on the right. And above that, we write a 1. Okay? And then we keep doubling the number for each step we make, okay? So the next 0 here is going to be 2. See if this is readable. Yes. Okay, and then 2, and then double it is going to be 4. And then 4, and then we double it is going to be 8. And we keep doubling, okay? So this is 16. This will be 32. This will be 64. And this will be 128. All right. And now all we have to do is we take a look at this number 1 and we see 1 is on. And basically on means take in the sum. And off is going to be skip. Okay? So what that means, if the number is 1, we would add it to the sum. So we write down 1. And then we add a plus to the left. And we see, okay, the second number, that's 0. So we skip this number 2. We go to the third one. We see, okay, number 4. And we see the binary number has 1. So we add 4. Add another plus. Number 8 has the number 1 in the binary. So it's going to be 8. We're going to keep adding this. We're going all the way down the list. Number 16 has a 1, so we add 16. Number 32, 0, so we skip this one. 64, 0, skip this one. And then the last one, 128, has a 1, so we're going to add that just like so. And now it's just as simple as adding these numbers together. So let's clear that here, make sure we're in decimal. And then we do 128 plus 16 plus 8 plus 4 plus 1. We can see the sum here. We click on equals 157. Okay, and then we go to binary and we check, is this the same as what we have? And we see 1001, 1101. And that's exactly the same. And that's how simple it is to calculate in binary. Let's say we have like 1111, 1101, 1000, 1110. Okay, so this is a larger number, but it's still going to be the same. We start on the right side and we move to the left. Okay, so we start here, we write down 1. This is going to be 2, this is going to be 4, this is going to be 8. Then we go here, that's going to be 16, 32, 64, 128. And then this number is going to be 256. And you would basically keep doubling the numbers, okay? That's how simple it is. Times 2, times 2, times 2. That's how simple it is. And then you can always convert a binary number to a decimal number as well. That's how simple it is. And you may be wondering, Loab, why did you teach me this? Well, in Cheat Engine, Reclass, and EDA Pro x64DBG, we're going to be working a lot with binary numbers and especially with hexadecimal numbers. And we want to just be able to at least understand what it is and how to convert them. Because when we're looking in Cheat Engine or Reclass, you want to be able to make like these small conversions in your head. Of course, for bigger numbers like this, we're obviously going to use a calculator, that's fine. But for smaller numbers, it's useful if you can convert them. So let's take, for example, the offset AC, for example. Then you know, okay, C, yeah, that's going to be 12 in this list. Well, we're going to do that times 1, because this is 16 to the power of 0. That's a bit too big. Okay, and then A, that's going to be 10. Okay, 10, that's going to be 16 to the power of 1, because it's the second number. Okay, that's 16. So we do 10 times 16. Okay, then we know, okay, 12 plus 10 times 60 is 160. Okay, and then 160 plus 12, that's going to be 172. And then you can check it, of course. Go to hex. AC. Well, of course, it's 172. So we can like quickly convert that in our head, and that's going to be very useful in your game hacking journey. Now that we've covered the foundational concepts, we're ready to embark on our game hacking journey. When we double click a game, our operating system, like Windows, manages the execution of the game by copying its executable file into RAM. It's crucial to understand that when we create cheats using memory editing techniques, we're manipulating the game in RAM. Changes made here are temporary, and if the game crashes, restarting it resets everything, since we haven't actually changed the files on disk permanently. But when we are editing files on the disk, we may permanently damage something and ruin everything. This is where virtual memory comes into play. So what exactly is virtual memory? The most basic explanation of a computer program is just a bunch of zeros and ones. But what do people mean by that? Well, let's take a look at this example here. This is what you may understand as a computer program, which isn't really a wrong idea of what a program looks like. It's actually very close. But instead, we group this mess into a total of 8 bits, like so. You can tell that this is much cleaner to look at, but it's also much cleaner to work with. It's important to note that 8 bits like this is exactly the same as 1 byte. So if we are working with Cheat Engine, know that this is 1 byte when selecting a data type. This would be 2 bytes. This would be 4 bytes. And this would be 8 bytes. The reason why we have these different sizes is for a very useful reason. By increasing the amount of bytes, we also increase the amount of storage a number can hold. The maximal decimal number of 1 byte is 255. This is enough for a variable like health, where health doesn't get higher than 100. But if we are storing money, for example, you may want to store this in 4 bytes or maybe 8 bytes. Because 4 bytes can store a decimal number up to 4 billion. And 8 bytes can store up to 18 quintillion decimal numbers. You now have a much wider range to play with. So maybe if your character can earn more than 4 billion in game, you may want to use 8 bytes, so he can store more money in that address. Let's say we are playing a game and we found out that the health of the player is stored in a 1 byte sized variable. We've also found out that this is the address of health. Well, we've just learned about binary, so we know we can change this number to increase our health. And by changing our health to 11111111, we know our health is now 255. Because this binary number converted to decimal is 255. It is therefore important to note that this binary number you see here is a value and it's not an address. Okay, so it's a value and it's not an address. Let's take a look at what the address is of this value. We start on the very top left, address 0. When we go one more to the right, we have address 1. And one more to the right is address 2. So if we keep counting up, we end up at the address 246. So what this means is that our health value 100 is stored at address 246. So just keep in mind that all the bits are actually values and the address is just the location where the value is stored. You can pretty much compare this with an array where each index is going to be the actual address and the number that's in the array is actually the value. Alright, so let's take a quick look at the different data types before we dive into the part where we learn about virtual memory and how it works. Well, it's important to understand this, and I recommend you to learn what is showcased right here. We've already learned that 8 bits is equals to 1 byte. And an alternative name for byte is uint8, and that stands for unsigned integer, and the 8 stands for 8 bits. It's important to know what these alternative names are, because we will be using these names in a tool named reclass. So for the people that do not understand what unsigned means, it's basically a way to use integers where negative values are not relevant, and it allows for a larger range of positive numbers. This is the range of an unsigned short, for example. But when I make this short signed, the range will also include negative numbers. But we can also see that it decreases the range of the positive numbers as well. This is because the first bit of a byte is a sign bit, which is used to represent if a number is going to be positive, number 0, or negative, which is number 1. So you can see that we now only have 7 bits to play with instead of 8 bits. That's why the range is smaller. So basically, unsigned is just a way of making the range start at 0 and only use the positive numbers and use a total of 8 bits instead of 7 bits. And if we make an integer signed, it also means we're including negative numbers. So the maximum value will decrease as well, as the minimum value is also lower than 0. Alright, we are ready to really delve deeper into virtual memory. Remember this image? For the sake of this video, we will assume that you are using the 32-bit version of a game. For example, Assault Cube. But what does 32-bit mean? Well, basically, the bit size refers to the memory it can access. We've got 32-bit and we've got 64-bit. A 32-bit system can reference 2 to the power of 32 bytes of memory, which translates to 4 gigabytes. On the other hand, a 64-bit system can access a mind-blowing 2 to the power of 64 bytes, which is roughly 4 billion times more than 32-bit. So again, we are going to assume that we want to manipulate the memory of a game that's 32 bits. If you've downloaded Assault Cube 1.2.0.2 in the previous video, you are running a 32-bit process. Let's take a look at what the game looks like in RAM when we double-click the game's exe file. When we launch a 32-bit program like Assault Cube 1.2.0.2, it gets its own virtual memory. For simplicity, let's focus on a 32-bit process running on a 32-bit system. limiting its addressable memory space to 4 GB. However, only a portion of this is available for the game's use. Let's say about 2 GB, as the operating system reserves the rest for its own needs. Imagine this memory block. If the game requires a minimum of 4 GB of RAM and the operating system reserves 2 GB for its own needs, it means that the game does not actually use 4 GB. Let's say it only utilizes 2 GB, leaving 2 GB for the operating system. Now inside this memory block we have the game's copied executable and we have 2 GB of free memory we can use. Let's first delve into the copied exe. This copied exe consists of 2 crucial components: data and game code. Data holds information that may be useful for our cheat, while game code can generate new data. In this visualization, the top part represents the game in pink. As the exe loads into virtual memory and executes its code, it starts loading various elements, such as the world and the heads-up display. Arrows pointing into nothing symbolize other potential objects like audio or maybe physics. Think of this as a small tree. In a real game, it's much larger obviously. Everything under assaultcube.exe is just data. In the exe file itself, it's a mix of game code and data. For instance, in the player object, we can find details about health, ammo, coordinates and so on. The enemy's object is similar, but with different values. So this is what the previous tree would look like in a memory block. We can see the assaultcube.exe section right here. And then we also see it pointing to world, and from world to player and enemies. Or this could be from assaultcube.exe to the heads-up display. All these colored objects are allocated memory. All the blank space we see is free memory, aka unallocated memory. When we remove all the allocated objects, it's called deallocated. It's important to remember these terms as they will come back more often in this series. What's important to understand is that every time after a game restarts, all the allocated objects are likely to be at a different position. After a full restart, the block may look like this. This is exactly what happened in the previous video, where I was showing you what happened after I restarted the game. The memory address we found was no longer valid, because the new health location was stored in a new address. We can see that with every restart on the game, the allocated objects are at a different address. So how can we make a cheat if the objects get loaded into different addresses each time we restart the game? This isn't reliable data to use in our cheats, right? Well, that's true. And in order to defeat this issue, we have to learn more about pointers and offsets. However, before we get to that part, we have to understand that this copied exe is in fact the only section in this memory that's reliable. Theoretically, this exe section is also able to load anywhere within this range. However, we can use the Windows API to always find the location of the copied exe in memory, and therefore this is reliable. This reliability makes it the starting point for most of the data we'll use. Now that we have an understanding of how virtual memory works, let's learn about the part that's difficult to most new game hackers: offsets and pointers. I will try my very best to explain it so you can understand it in one try. Okay, so what is a pointer? A pointer is a variable that contains a memory address as a value. Let's take a look at this simple memory overview so we can understand it better. In the left column we have addresses, and in the right column we have the value. In the first row we have the memory address 0x1000 with a value of 100. Completely normal. This is what you've seen in the previous video in Cheat Engine. Now let's go to the second row, and there we have the value 0x1000. We can see that this 0x1000 is a hexadecimal number, which means that this is an address. And if we compare that to the first row, we can see that 0x1000 is the address of the first row. That's all a pointer is. It's a value that happens to be an address. So what does a pointer look like in C++? It's actually not that difficult. First we declare a variable, such as int health equals 100. You can read this line of code as integer named health is set to 100. This is the easy part. Next up may be a bit confusing, but it's actually pretty simple. In order to create a pointer to health, we would do it like this. int star, and then we give it the name pHealth equals end% health. So let's read this in normal English again. Integer pointer named pHealth is set to the address of health. Here the star stands for pointer and the % stands for the address of. So we can see in this example that the pointer is just a variable from which the value happens to be an address. Let's take a quick look at this picture here. The arrows we see here are pointers. In this case we have 3 arrows, which means that this is a 3-level pointer, which is also known as a multi-level pointer. A multi-level pointer is a pointer that points to the memory address of another pointer. In this code it would look like this. We can see that we have a second pointer with 2 asterisks, and it holds the address of the first pointer. This is a multi-level pointer, but when a pointer points directly to a variable, it's a single level pointer. Alright, so let's say we want to find coins. It seems like the coins are located in the last section, the inventory. So this is a technical overview of what a multi-level pointer may look like. Let's learn how it works. We start on the very left. We can see the copied exe file that's loaded into memory. And all the way to the right we have the inventory. Underneath these objects we also have different rectangles with hexadecimal numbers and offset names. We notice things like player health, player X and player Y. But what are the numbers on the left of them? These are what we name offsets. An offset is like a distance that tells you how far of where something is located from a starting point. And in this case, it's the module base address of the executable game. For instance, in computer memory, it can indicate how many bytes or bits you need to move from a known location to find a specific piece of data. Offsets are commonly used in programming to access elements in arrays, structures, or memory regions by specifying their relative position to the starting point. This example will hopefully make it simple for you to understand. We have a starting point. Let's say that's our house at point A. And then we have the offset B, which would be the distance we have to travel in order to get to our destination. Let's say it's about 15 kilometers. When we travel that full distance, we end up at our destination, like the supermarket. This overview works exactly the same. We start at a copied game in RAM and we go down 4 bytes, and we will end up at player X. If we then move 4 more bytes down, we end up at player Y. Alright, so let's start again. We are here at the start again, and we now have to go down 12 bytes. If you remember from earlier, we know that C as a hexadecimal number converted to decimal is 12. This is an example of why it's handy to learn about converting. So by going down 12 bytes we end up at world star, and we know a star shows that something is a pointer. So this is a world pointer. When we follow this pointer, we end up at the starting point of world, and from here we can go down 4 bytes again. We have now located the height of the world. If we move 4 more bytes, we see a player pointer. Follow that pointer and we are now at the starting point of the player object. Now we move 4 bytes down and we end up at the inventory pointer. Follow that pointer and we have now arrived at the final inventory object. The only thing we have to do now is move 4 bytes down, and then we have successfully found the address of the coins we wanted to hack. We can use this combination of starting points and offsets to find ourselves reliable paths towards the coin. This strategy will always guide us to the right coin's address, even when we restart the game. If we then want to modify the value that we found in the address, we then just have to call the write process memory and write a new value into that address. Well, that's pretty much the game hacking fundamentals explained in 40 minutes. If you still have some questions about anything I've covered today, I highly recommend you to join the Discord, and there you can either ask me or the community. If you want to try it out yourself, I would highly recommend watching the series of Zachary, named CS420. Many examples I've used today are inspired from his series. If you want to learn more about pointers, I highly recommend you to watch the videos of the journal and low-level programming. All these resources are amazing. I want to thank you for watching. It was a pain in the ass to make this video, but it's finally finished. In the next episodes, we're finally ready to get started with some juicy game hacking stuff in Cheat Engine and Reclass. Have a good day, and I'll see you in the next one.